Hi, my name is Alique Momjian, and I'm a biomedical engineering undergrad student at UC Davis. And my project is about modeling of cerebral vessels from time of flight MRI with intracranial atherosclerotic disease. So some background on ICAD and computational fluid dynamics. Intracranial atherosclerotic disease, or ICAD, is characterized by plaque buildup in cerebral blood vessels. And these stenoses are located at areas with low wall shear stress, which we can see in areas of vasculature with greater lumen diameter or bifurcations. However, it is very invasive to measure wall shear stress in vivo, and this has halted our ability to diagnose ICAD for some time. A solution to this problem is computational fluid dynamics, a non-invasive method of modeling vasculature from imaging data and simulating blood flow. We can use CFD to gain non-invasive measurements of wall shear stress, velocity, and pressure to diagnose and predict locations of ICAD stenoses. Here we see a pipeline of running such a simulation in the subperson vascular. We start off by using time of flight MR data, and we see in this picture a maximum intensity projection from one of our subjects' time of flight data. We can create a model, discretize it into fine pieces, and then after inputting inflow and outflow boundary conditions, we can use the Navier-Stokes equations to simulate flow. So my summer research has been focused on the second step of creating a model. Cerebral arteries are relatively small vessels, especially compared to coronary arteries, and are difficult to model as a result. They cannot be automatically segmented. Our purpose is to determine the most efficient and robust modeling technique in synvascular, and the three methods that we compared are the 3D thresholding method, the 3D level set method, and the 2D contouring method. Our goal was to segment the entire circle of Willis. Our inlets are the internal carotid arteries and the vertebral arteries, and our outlets would be around 2 to 5 branches off of the middle cerebral arteries, the posterior cerebral arteries, the anterior cerebral arteries, and the superior cerebellar arteries. So the materials for this project, we analyzed 3 subjects, 1 healthy control and 2 patients. Our first healthy control was a 71-year-old man, and our second patient, our first patient has a congenital narrowing of the right vertebral artery and is a 50-year-old female. And our second patient is an ICAD patient with stenoses in the basilar and the left vertebral arteries. You can see the location of the stenoses circled in red. We use time of flight MRA on a 3 Tesla MRI system with spatial resolution of just over 0.5 millimeters isotropic. So the first method that we will analyze is a 3D thresholding method. The steps to create a model using this method is to first input a starting point. In this picture, you can see that the starting point is at the bottom of the basilar. Now, if your model has multiple inlets, such as mine, you still only need to choose one starting point for your model, even if you have multiple inlets. The next step is to choose a signal intensity threshold. Signal intensity characterizes the brightness of voxels, and the threshold tells the software the range of voxel intensities to consider as vessel. Our range for this project is typically between 100 and 200 for the minimum of the threshold. And the maximum of the threshold should be the maximum signal intensity of voxels seen in your imaging. The software will then build a model by region drawing voxels within this signal intensity. You can see our result from creating a model with the 3D thresholding method here, but as you can see the voxels in the walls, it's a little blocky and must be smooth to get our final product here in the bottom right. Our next method is the 3D level set method. So similarly to the 3D thresholding method, you choose one starting seed, but this time you get to choose multiple ending seeds. Now, again, if you have multiple inlets, such as my model, you still only need one starting seed, and your other inlets can be marked with ending seeds. It will not matter in the long run when we input inflow and outflow boundary conditions. You will just put inflow boundary conditions to all your inlets, regardless of whether they were starting seeds or ending seeds. So no need to worry about that. Once again, we will choose a signal intensity threshold similar to the 3D thresholding method. But the difference is that this method uses the level set function to create a model which works by building a surface at the region of greatest gradient magnitude or the steepest signal intensity change, which will occur at the borders of vessels, as you will expect the bright voxels to be contained in the vessel, and then the dark voxels will be on the outside, and we will see a great change in signal intensity right at the border. So our last method to analyze is the 2D contouring method. This method is much more manual. It requires the user to manually place points along the arterial course to path out the vessels, which will then be used in the second step when we draw 2D contours perpendicular to the path in order for the software to loft a model in this last picture. We use circular contours for our contouring method. This allowed us to automate the process a little bit. We were able to copy paste 2D contours between slices that had similarly sized vessel lumens. This sped up the process and made it much more automatic. So to compare our three methods, we will first look at our healthy control. So first thing we notice is that the 2D contouring method has 2 outlets per main vessel. This was intended for our model, as I stated previously. In contrast, the model created by the 3D thresholding method has far more than 5 outlets. As we can see on the middle cerebral arteries, we have a whole branch of multiple out branches and outlets from the middle cerebral artery. We can also see the same on the anterior cerebral arteries and the posterior cerebral arteries in the back. We also see that the boundaries have been tapered off to a point rather than being capped off due to smoothing. This is a big issue because we expect our model to end with caps where we have outlet conditions. If we don't have a cap there and we have a point, then our boundary is not accurate and we can't prescribe boundary conditions to that at all. This is a big problem with this model. Lastly, with the 3D level set method, we see that the entire left internal carotid artery is missing. And the right anterior cerebral artery is also missing. The left anterior cerebral artery also has a gap in it, as you can see by this blue circle. We also see that the right posterior cerebral artery is incomplete, and we do not have enough branching per main artery. Next, we will look at patient 1, who has a congenital narrowing of the right vertebral artery, as is pointed out by the stenosis. We notice that the 2D and 3D contouring methods produce models with similar amount of branching. We have however, again, with the 3D thresholding method, we have thinning outlets due to smoothing. The 3D thresholding method was not able to segment the narrowed right ICA. Neither was the 3D level set method able to do that. We also see noticeable holes in the internal carotid arteries of the 3D thresholding method model. The 3D level set method missed most of the left vasculature and, again, did not segment the narrowed right ICA. Lastly, we will look at patient 2. This time, all 3 methods were able to demonstrate stenoses, which is very important to analyze ICAD. Again, we see thinning and excessive branching depicted on the 3D thresholding method. The 3D level set method, as we can see by the slice indicated by the blue arrow, produces greater vessel diameter than the other 2 methods. In fact, when analyzing this point pointed at by the blue arrow, we see that there's a 94% increase of diameter from the 2D contour to the 3D level set in the basilar upstream of the stenosis. And we also see inaccuracies such as merged anterior cerebral arteries. Again, we were not able to get enough branching on the right middle cerebral artery. And in contrast, the 2D contour method has the desired amount of branching, about 2 to 3 branches per main artery, and has smoother walls and cleaner curvature. Some additional results is that the 3D thresholding method and the 3D level set method took minutes, whereas the 2D contouring took hours of manual human work. However, we were able to improve the 2D contouring process by using an automated method of using circular cross sections and copy pasting them when we see similar lumen diameter across slices. We were also able to somewhat vary the extent of segmentation via the 3D thresholding method by altering the signal intensity threshold minimum. Since this is the only way we can really control how many branches are included. If we choose a high minimum at 196.8, we see that there are far less branches, and in fact, the entire anterior circulation was not included. because the posterior communicating arteries were not included using this signal intensity. We lowered it to 155 and still missed out on the anterior circulation, but saw more branching. We can see a more complete left superior cerebral artery here. And then if we drop the signal intensity minimum even more, we can finally see the anterior circulation. But then again, we have more branching than we need, and this is the most we can do to alter this model. To conclude, the 2D contour method was the most accurate and allowed us the greatest control to create clean, smooth models with exactly the region of interest. So in the future, we want to actually run simulations. And in order to do that, we need to have inflow and outflow boundary conditions. And one thing that is very important for our project is to use patient-specific boundary conditions. We want to avoid using literature as much as possible because our subjects have stenoses and there's possibilities of revascularization in the circle of Willis due to stenoses. So we want to take into account this fact by using patient-specific boundary conditions by scanning our patients ourselves. So in order to get inlet flow rates, we want to use phase contrast MRI. From phase contrast MRI, we can gain inlet flow rates to get the flow velocity in the internal carotid arteries and the vertebral arteries. And to measure outlet resistances, we can use cerebral perfusion from arterial spin labeling MRI and the vascular perfusion atlas to calculate flow rates in the posterior cerebral arteries, the superior cerebellar arteries, the middle cerebral arteries, and the anterior cerebral arteries, which I've highlighted in the image with corresponding colors to their region in the atlas. And then we can split flow using Murray's law from there to calculate the resistance of each outlet. So these are the references that I used for the project over the summer. And I also want to thank everyone involved in this project. This project could not have been completed without you guys. And that concludes my presentation. Thank you everyone for listening.